Hello everyone, my name is Suai Tong. I'm a postgraduate student at Tianjin University. The topic of my thesis is multi-intention oriented for sequential recommendation. My presentation is divided into these four parts. Sequential recommendation aims to capture users' dynamic preferences from their historic behaviors, which can make a next item recommendation. However, when the training data is limited, traditional methods may fail to infer appropriate user representations. Presently, contrastive learning is gradually applied to sequential recommendation, which mainly contains two key components: data augmentation for enhancing training data, and contrastive losses for enhancing self-observation signals. The two views obtained from the same user behavior sequence must be similar. Therefore, data augmentation methods can alleviate the data sparsity issues. It can extract more meaningful user patterns and further encode the user representation effectively. However, they may amplify noise in the original sequence and modify original sequential patterns. Now let's take an example to briefly illustrate. In practice, the user selects each item based on underlying intention, which can be understood as a subjective reason for the interaction, such as preparing birthday gifts, buying travel gear, passing the time, and so on. If the current intention is to prepare birthday gifts, then items related to other historical intentions are regarded as noisy. After data augmentation, in one view, noisy behaviors may introduce items that the user doesn't care about at the current moment. Moreover, the other view also modifies sequential patterns which can change the user's current intention to prepare birthday gifts. Therefore, two views without considering multi-intention conditions differ significantly, which limits the performance of contrastive learning in sequential recommendation. So we formalize the denoising problem by selecting the user's current main intention. We create high-quality views by extracting multi-intention representations from augmented sequences. A novel design of sequence encoder can better create intent-level positive pairs. In this way, IOC-REC can separate different intentions of the same user so as to select the user's current main intention in the denoising process. So in our paper, we expanded solutions to a few major points. First, we propose a novel framework, IOC-REC. This is the first work to apply intent-level contrastive learning for denoising problem of the sequential recommendation task. Then to create high-quality views with intent level, we fuse local and global intentions to unify sequential patterns and the intent level self-observation signals. We designed the sequence encoder in IOC-REC, which includes three modules: local module, global module, and the disentangle module. The global module can capture users' global preferences, which is independent of the local module. The disentangle module can obtain multi-intention behind the global and local representations. Next, IOC-REC can jointly optimize the contrastive learning objective and the sequential recommendation objective. In the contrastive learning task, we separate different intentions of the same user so as to select the user's current main intention in the denoising process. Finally, our method achieves excellent performance among compared methods. Now, this figure shows the overall framework of the proposed method, IOC-REC. It includes the sequence encoder and multitask training strategy. Now, from a local perspective, the local intention representations are inferred solely based on individual sequence, and the test to focus on more recent activities. So we feed the input embedding into a series of stacked transformer structures as our local module. From a global perspective, especially in augmented sequences, it is difficult to distinguish noisy information in one sequence. So we introduced a learnable query matrix shared by all sequences so that more available information can be utilized for the prediction at each step. In this way, the global module can capture more semantic information from all sequences to better distinguish current noisy items. The disentangle model is appended after local and the global module so as to reuse their expansive power. According to the distance between the sequence embedding and a set of intention prototypes, we disentangle the user preference into intentions. In addition to relevance with PKI, we also consider attention with PI to measure how likely the intention at position I is essential for predicting the user's next intention. Finally, we apply intention disentangling instead of intention aggregation. We disentangle the user's representation for each position I in a sequence SU under K latent categories according to PKI and PI. In the contrastive learning task, data augmentation operators are first required. Random augmentation operators include crop, mask, and reorder. Informative augmentation operators include substitute and insert, which employ item-based collaborative filtering considering inverse user frequency to measure item correlations. The last is multitask training. The set A includes about 5 data augmentation operators. As shown in this figure, it first augments a sequence as a positive pair with random select 2 augmentation operators from set A. Then it encodes the sequence by concatenating embedding outputs from the sequence encoder. Finally, view 1 and view 2 mean that we add the global and the local representation from the same intention prototype. Thus, we get intent level representations for each augmented sequence. With intent extraction from the sequence encoder, we can obtain 2n times k intent level positive pairs in a mini batch of U1, U2, and UN. We treat each pair as UAI and SUAJ as a positive pair. Then the other 2 times k minus 2 intent level augmented sequence are considered as the negative samples for this pair. In the sequential recommendation task, the left side shows the next item prediction. In a sequence, we map the main intention at the current position T for each positive and negative sample during the training stage, so as to select the main intention of the current user to predict next item. To leverage the intent level self-supervised signals derived from the labeled raw data to enhance the performance of sequencing recommendation, we adopt a multi-task strategy. The 3-part experiment. First, table 1 shows the IOC-REC achieves state-of-the-art performance against a series of baselines for data size. According to CL4S-REC, this column random adopt crop mask reorder to augment all sequences. Will this column, according to COSE-REC, we randomly adopt a substitute, insert, and mask for short sequence with less than 4 iterations, and randomly select all 5 augmentation operators to augment the long sequences. This metric includes hit ratio and NDCG. IOC-REC fuses multi-intention into sequential recommendation model by a new contrastive learning, which helps the encoder discover a good semantic structure across users' behavior sequences. The IOC-REC consistently outperforms existing methods on all data size, showing the necessity of extracting multi-intention oriented contrastive learning for denoising problems. Then to evaluate the role of multi-intention contrastive learning, we randomly select 2,000 users to visualize multi-intention representations. This figure shows different colors represent different intentions. IOC-REC can better distinguish the main intention and other intention for predicting the next item. Finally, this is ablation study experiments. Table 2 reports the performance comparison between ILC-IEC and its three variants. Without local intention, the performance of the ILC-IEC decreased significantly. This also shows that under the influence of only the global intentions, it is difficult to accurately capture the user's current intention. Moreover, we additionally add the disentangle module based on two baselines respectively. When introduce disentangle module, we select the best intention on the data site respectively. So ILC-IEC obtains the best performance against these variants on 4 data sites. To sum up, we propose ILC-IEC to get the denoising process. Firstly, we design a global module to capture users' global preferences, which is beneficial in fitting well with the local module. Secondly, we investigate module to reuse global and the local module, especially to improve the performance of sequence encoder, sequence recommendation. Finally, ILC-IEC enhance the role of contrastive learning by considering the construction of poster pairs and the intent level. Extensive experiments show that ILC-IEC performs better than other methods in all metrics on 4 widely used real data sets. That's all. Thank you for your listening.